This talk will describe and showcase how Planet is building a next-generation analysis-ready dataset characterized by an enhanced level of sensor interoperability and data readiness to unlock the full potential of rich multi-sensor datasets. So the rise of the CubeSat and distributed constellations are part of a geospatial data revolution with potentially far-reaching societal and economic implications. The Planet employs a fleet of 100 plus nanosatellites to meet competing demands of both very high spatial and very high temporal resolution. This has enabled near-daily monitoring of the land surface in 4 spectral bands at 3 meter resolution globally. And combined with public mission data, this really represents a game-changing opportunity for medium resolution Earth observation. However, in order to realize the promise of remote sensing, we really need to improve sensor interoperability, cross-sensor consistency, and data readiness, which can be a real challenge when working with data from multiple sensors with different radiometry, quality, and resolution characteristics. For example, as shown here, NDVI from different generations of Planet's CubeSats in comparison with Landsat and Sentinel-2 can be like apples and oranges, which can become a severe obstacle using the data for analytic purposes. So Planet is pioneering advanced techniques to harmonize, clean, intercalibrate, and fuse data streams from multiple sensors to overcome these obstacles and to produce consistent, comprehensive, and sensor-agnostic data. We apply an adaptive version of the CubeSat-enabled spatial temporal enhancement method for this purpose. The so-called L3H processing ingests data from multiple sensors to produce a data product that inherits the best traits from each sensor while ensuring radiometric consistency with a selected code reference. The process produces a high-quality next-generation analysis-ready data product that will be suitable for analytical and data science purposes and align well with ground-observed spectrometer data. Applied to the study case shown in the previous slide, using Landsat 8 as the code reference, this is how it looks. The time series plot on the right, the circular symbols represent the L3H NDVI results that provide enhanced consistency with public mission data while taking advantage of high-frequency CubeSat observations to produce a clean and gap-free NDVI reconstruction. And this animation visualizes the challenges of working with multi-sensor data streams for an AOI in South Africa, highlighting temporal and spatial inconsistencies due to cloud contamination, gaps, and the fact of having sensors with different spectral responses and spectral bands. And this is how it looks after L3H processing and curation using advanced cloud masking, harmonization, gap filling, and sensor data fusion to produce a clean, metrically harmonized, and uninterrupted surface reflectance data feed. So this summarizes the key features of the L3H product. It will ingest the level 1 top reflectance data and perform advanced radiometric harmonization, taking advantage of highly calibrated third-party sensors for full fleet interoperability. It will include rigorous temporally driven cloud and cloud shadow detection and will fuse in MODIS, Landsat 8, and Sentinel-2 data to fill gaps in planoscope coverage. It will also include extensive QA information to ensure pixel traceability and report on the confidence of gap-filled data. Ground validation is a critical component of L3H production and evaluation. A key objective behind the L3H is to remove obstacles that have traditionally challenged the notion of remote sensing as a trustworthy source for delivering useful and actionable insights. And this requires extensive evaluation against ground-based spectrometer networks, and we currently engage in a ground validation campaign with Arable for that specific purpose. The figures to the right showcase NDVI time series or one of these locations, intercomparing the ground data with L2 and level 3H surface reflectance data from Planet. Clearly, the L3H processing helps clean up the data and ensure a significantly improved agreement with what is being observed on the ground. And this example shows that with L3H data, we can start to reliably identify subtle daily changes in vegetation dynamics and plant health in response to treatment differences. And note that the L3H recorded NDVI response is almost identical to the in-situ based record. So to summarize, Planet is building a next-generation analysis-ready sensor fusion dataset that is enabled by high-resolution CubeSats and powered by machine learning, leveraging rigorously calibrated third-party sensors for full fleet interoperability. The enhanced level of data readiness and spatial temporal consistencies of the L3H will help unlock the full potential of these rich multi-sensor datasets.